Next, we want to develop a strategy for dealing with powers of tangent and secant. So in this example, we see we have tangent to the 6th times secant to the 4th. So if we're thinking about developing a strategy, we might want to consider what we did in a previous example where we were able to break off some factor and save it later for a substitution. So in this case, what might be a good factor to save for substitution? Well, in the case that we were substituting tangent, then we want to think what would be the derivative of tangent. Well, we would need to save a factor of secant squared if we were to substitute tangent. On the other hand, if we were to substitute secant, the derivative of secant is secant x tangent x. So then we would need to save a factor of secant x tangent x. So what would be the best strategy in this case? Well, because here I see that we have an even power of secant. When I break off a factor of secant squared, what will remain is another even power of secant. And so that remaining power can be rewritten in terms of tangent using our identity 1 plus tan squared equals secant squared. Okay. So our strategy here will be to split off a factor of secant squared. So we'll have secant squared times secant squared. And we're going to save this secant squared for substitution, because we notice that if I can rewrite the remaining factors in terms of tangent, then we can substitute tangent, and then that secant squared will become du in our substitution. And we see that's going to be possible in this case because we've got this factor of secant squared here that we can rewrite as 1 plus tan squared. So I'm going to rewrite this as tangent to the 6th. Secant squared will become 1 plus tan squared. And then the secant squared dx will save, because now I can substitute tangent. All right, now I notice that if I let u equal to tangent, then we can get u to the 6th plus times 1 plus u squared. And then the secant squared here becomes our du. So I'm going to let u equal to tangent, tan x, and then du will be secant squared. So now our integral becomes the integral of u to the 6th, 1 plus u squared, du. Now it's a simple polynomial integral. Before I integrate here, I'm going to distribute the u to the 6th. So we get u to the 6th plus u to the 8th. And so now I'm ready to integrate. So it becomes 1 over 7 u to the 7th plus 1 over 9 u to the 9th. And then putting my u back in, which was tangent. So we'll have 1 over 7 tan to the 7th plus 1 over 9 tan to the 9th. And there we have it. Here again we have another integral that involves powers of tangent and secant. Although what I notice here is that we have odd powers of tangent and secant. So if I want to develop a strategy for this one, what might help is to think of what happens when I break off one of the secant and one of the tangent factors, so that we can save a secant tangent. Then what remains is we'll have an even power of tangent and an even power of secant. And in particular, we'll have an even power of tangent that can be rewritten in terms of secant. So we can kind of think about now setting it up for a substitution with secant. We know that the derivative of secant is secant x tangent x. So by saving one of the factors of secant and one of the factors of tangent, then what remains just has to be rewritten in terms of secant. And we'll see that's possible because then we'll have an even power of tangent that I can rewrite in terms of secant using the identity tan squared plus 1 equals secant squared, so tan squared is secant squared minus 1. So we'll kind of think about how this strategy is going to play out here. Okay, so the first thing we said was we'll split off one factor of each. So I'm going to take one factor of tangent and one factor of secant. So we'll have tan fourth secant to the sixth, and then secant x tangent x, or secant theta tan theta that we're saving. So this is the piece that we're going to save for the substitution. And then my goal is to try and rewrite the remaining stuff in terms of secant. So the tan to the fourth here, now my goal is to rewrite in terms of secant. And that's where this identity tan squared equals secant squared minus 1 will come in. Okay, so tan to the fourth, I'll rewrite that as tan squared squared okay, and then tan squared becomes secant squared minus 1. Okay, now we've rewritten everything over here in terms of secant, so now we're ready. Oh, and there should be a square there. I don't want to forget. So now we're ready to substitute secant. So let u equal to secant theta. So then du will be secant theta tangent theta. So that's the secant theta tangent theta that we saved over here. That becomes du. And then here we'll have u squared minus 1 squared. And then u to the sixth. And then all of this becomes du. So now we're left with a simple polynomial integral. I'll do a little bit of foiling and distributing though before we can integrate. So let's FOIL out u squared minus 1 squared. Be u to the fourth minus 2u squared plus 1. And then the next thing I will do is distribute u to the sixth. So I'll have u to the 10th minus 2u to the 8th plus u to the 6th. And then I'm ready to integrate, so this will become 1 over 11 u to the 11th minus 2 over 9 u to the 9th plus 1 over 7 u to the 7th. And then finally putting the u back in, we'll have 1 over 11 secant to the 11th minus 2 over 9 secant to the 9th plus 1 over 7 secant to the 7th. Okay, so in the last two examples we saw two very similar strategies. One was setting it up so that we could substitute tangent, or as we saw in this one, we were setting it up to substitute secant. And here's the just a broad overview of those two strategies. So we see that the first strategy would work anytime we had an even power of secant. So if the power of secant is even, Then we can save a factor of secant squared, and then use the identity secant squared equals 1 plus tangent squared to express the remaining factors in terms of tangent. And then we can substitute tangent. Or as in the last example, if the power of tangent is odd, then we can save a factor of secant x tangent x, and then use the identity tan squared equals secant squared minus 1 to express the remaining factors in terms of secant x, and then substitute u equals to secant x. Okay. Now, this doesn't cover all cases, so the other cases would be a little bit less clear-cut. But we can perhaps see those in another example. So, other cases may want to use different identities. We may want to use integration by parts, or trying to be a little bit tricky with it will be helpful. Here are some other useful formulas. We proved this formula back in chapter 6, that the integral of tan x by itself is just ln of the absolute value of secant x. Or if I want to integrate secant x by itself, that will be ln of secant x plus tangent x.